I wish people would take these issues a bit more seriously and treat them as sort of not just an afterthought, but one of the sort of central concerns that you should be thinking about when you're trying to solve the measurement problem. That really the measurement problem is in some sense all about understanding how to tell a consistent story about how our experiences and our outcomes, our measurement outcomes, are connected to the sort of theoretical entities.
So welcome everyone to today's interview, where I'm very pleased to welcome Professor Emily Adlam. She is Assistant Professor of Philosophy at Chapman University, and her work focuses on physics, especially quantum physics and the philosophy of physics. And her books include Foundations of Quantum Mechanics, Constructive Axiomatics for Spacetime Physics with Niels Linnemann and James Reed, and Saving Science from Quantum Mechanics, the Epistemology of the Measurement Problem. That last book will be the focus for our discussion today. But yeah, she also has a variety of published articles on these and related topics. Feel free to add anything, but with that, welcome and thanks so much for being here, Professor Adlam.
Yeah, thank you very much for having me. I'm looking forward to it.
Awesome. So yeah, as I said, we'll be discussing your new book, and I'll include links to where people can find this from OEP or Amazon or wherever in the description. But it's called Saving Science from Quantum Mechanics, the Epistemology of the Measurement Problem. Yeah, so I don't know, when I heard about the measurement problem, and I think standardly when people think about it, it has something to do with, well, not something to do with epistemology, really, not all that significantly, right? It has more to do with, well, what counts as a measurement and how do those result in definite outcomes, despite how we think quantum theory works. And so, yeah, maybe if you could start by talking a little bit more about the measurement problem and why you think it does have these stronger implications for epistemology and science more broadly.
Yeah, so the measurement problem, as you say, is connected to the issue of trying to understand what is happening during a measurement in quantum mechanics. Basically, the worry is that quantum mechanics seems to have sort of two separate formalisms. It has the standard unitary Schrödinger equation evolution, which is what happens most of the time. And then it also seems to have this thing that is called wave function collapse, where when you perform a measurement, the wave function sort of collapses down to one or two out of all of the possible outcomes. So there's two different processes going on. We don't have a sort of full story of how they fit together, and we'd like to understand better, how these things are related to each other. Is wave function collapse a real thing, or is it some kind of artifact of the way of thinking about things? What's happening here? So so standardly, I think people often think about it as a problem of sort of ontology, trying to sort of understand what's really going on, what's really there. And I think that is certainly part of the problem. But I like to think about it in terms of epistemology because of the nature of measurement and the sort of the special role that measurement as a category plays in our sort of ways of thinking about physics. Because, measurement is not just any old kind of physical process. Measurement is sort of the point at which our experiences make contact with the world. It's where all of our data comes from. The term measurement here is sort of used quite generally in quantum mechanics. So really sort of any observation of the world could potentially be a measurement in this sense. And so that I think makes the measurement problem really weighty, not just about as a sort of ontological issue, but as a sort of epistemic issue. Because if we don't understand what's happening during a measurement, then we don't really understand the connection between our theory and the experiences that are supposed to be the evidence for that theory. And so to have a sort of fully coherent story about the theory and how we can have come to know the things we think we know, we need to be able to sort of understand clearly what is a measurement, what happens in a measurement, and how does this process of measurement sort of connect us with the things in the world that we're supposed to have been able to find out about by measurements.
Fascinating. So, do you think the problem there concerns only or primarily measurement in quantum mechanics, or does it impact science and inquiry more broadly, do you think?
Yeah, so I think it sort of depends on how you sort of think about approaching the measurement problem. So as part of the issue is that it seems as though there's some kind of distinction or cut off between the classical world and the quantum world, and there's all sorts of weird things going on in the quantum world, and then things are more normal in the classical world. But we don't know exactly where that boundary falls or when one gives way to the other. And there are some interpretations of quantum mechanics which suggest that there isn't really any such boundary. Many worlds interpretation, for example, says everything is really just quantum, nothing collapses, we don't get a transition really to a purely classical world. And so that does mean that worries you might have about the measurement problem are potentially a lot more general, because if the many worlds interpretation is right, for example, then it is indeed true that more or less any interaction you have, more or less any observation you make is in fact a quantum measurement. And so if we don't understand how quantum measurement works, we also don't understand how any other measurement works. And so there's a sort of problem here at the heart of our understanding of how it is that we're sort of interfacing with the world that we're trying to study. And as long as you don't have a complete solution for the measurement problem, you can't sort of rule out that kind of possibility. You don't know that the many worlds interpretation is wrong, so you don't know that you can sort of rely on your classical measurements to be just classical and simple and reliable.
Right, and we'll definitely get more into writing theory and different approaches here that you discuss in the book. But I just want to cover a couple of different initial responses that some people might have. Like, what if someone were to say, look, theory just still works, regardless of whether we have some worked out account of measurement. I'm still able to predict the outcomes of experiments and so forth. What do you make of this more, kind of pragmatic, shut up and calculate sort of attitude?
So there are certainly circumstances in which shut up and calculate is the right response. Sometimes we just want to do practical things with the theory and apply it to certain, sort of engineering problems and so on. It does work very well for those things. So certainly there's nothing wrong with doing that under appropriate circumstances. But at the same time, there are certainly cases where I think it is important to ask about these epistemic questions as well. Not least because, we still have a lot of scientific problems around how to expand quantum mechanics to other regimes or how to combine it with other theories. And you might naturally think that some of the problems we have come from the fact that we don't right now have a sort of full grasp of what is actually going on with the theory, and in particular how this process of measurement is supposed to work. So one can't necessarily anticipate in advance, but it seems to me reasonable to think that at least some of the problems we're facing as we try to sort of go on to new physics are partly to do with the fact that we didn't understand the original theory properly. So there are good reasons, I think, to care about these kinds of epistemic questions, even if they're not always going to be directly relevant to sort of pressing engineering questions.
Right. I mean, we can still ask these questions about what the theory is saying or what's true about the world and beyond what we need to calculate and predict certain results and so on. It seems right, and maybe it's important to do so for other reasons that you discuss. Okay, I had another question about measurement, and I was thinking about how to best frame this question, but hopefully I do it well enough to understand what I'm getting at. What if we say that, look, there's different senses of the term measurement. There's maybe in a more everyday colloquial sense, and then maybe there's a use of the term as it appears in quantum theory, but they may not be the same term or same concept at play there. And the idea might be that what concerns we might have about the quantum mechanical sense don't necessarily significantly concern the colloquial sense, and so need not significantly undermine science or inquiry more broadly. And I guess maybe, and I don't think what I'm saying here is to suggest a kind of Heisenberg cut, although maybe you could comment more on this. See what I'm getting at? What do you think about this?
Yeah, so I mean, certainly I would expect that a sort of full and satisfactory solution to the measurement problem is going to tell us that, as a matter of fact, the kinds of things we're used to thinking of as measurement in the classical world, roughly independent of the details of quantum mechanics, and that they're all sort of reliable in the way that we expect they are. For example, it seems clear that decoherence has something to do with this, that when you get into a regime where decoherence is important, most of the sort of central quantum effects are sort of averaged out and aren't relevant. So my thought here isn't that, perhaps quantum mechanics is really interfering with these things in a way that we don't expect. I don't think it is. I think they are effectively classical. But the worry is that we don't yet have a full story of how we get from the quantum world to this quasi-classical regime where measurements are just sort of reliable and work in exactly the ways we expect. And as long as we don't have that story, there's room for doubt that things are working in the way that we expect. And so we don't sort of have a fully coherent story about the world and our interactions with it, either in the classical regime or in the quantum regime, until we sort of have an answer to this question of how these measurements are supposed to work and how classical regimes sort of emerge in a complete way out of the quantum regime.
Right. Okay. That makes sense. And then, so would you say that the ordinary sense or everyday sense could be sort of, bootstrapped, treated as sort of provisionally fine until theory later explains how it works or vindicates it? Or do you think that science already kind of lacks warrant, or there's already a problem without understanding of how it works in this quantum sense? And maybe you could talk a bit more about your bootstrapping picture of scientific epistemology here.
Yeah, so this is an idea inspired particularly by some of Ha-Seok Chang's work on progressive coherentism. The thought being that sort of the structure of scientific inquiry and inquiry about the world more generally is that we sort of start out with some rough assumptions about the reliability of our means of inquiry. We sort of assume that when we do measurements, we're getting meaningful information about something that's out there. We assume that, we can collaborate with each other and work together to arrive at a full theory and that kind of thing. And, from when we start, we don't know any of that stuff for sure. We don't know the nature of the physical processes that are involved. We don't know what we're finding out about when we measure. Those are kind of sort of articles of faith that we start with. And I think the hope and expectation is that as we go on and we do science, the scientific theories we discover by using these means of inquiry are going to kind of affirm and make precise the original assumptions we started with. So the theory that you arrive at should say something like, yes, the means of inquiry you have used to arrive at this theory are in fact reliable and are in fact capable of teaching you about the things that you claim to have discovered using them. If you arrive at a theory and what the theory says is, no, you couldn't possibly have discovered that theory by the means that you have used to arrive at it, something has clearly gone wrong there. So there's a need that as we sort of go and build the structure of science up progressively, it should be coherent. What we eventually arrive at should perhaps not affirm everything we started with, but should affirm enough of our starting assumptions that we can understand how we could have arrived at it using the means that we have used.
Right. So we don't want the theory we arrive at to undermine the very way we got to that theory in the first place, among other things. Yeah, so I guess, so what do you think, maybe this question should be more towards the end, but I'll ask it now anyway. What sort of impact do you think that the concerns here should have on current scientific practice? I mean, it feels to me like maybe scientists don't take these concerns or don't recognize these concerns all that much about the epistemology here. Maybe, what do you think they should be doing instead?
Yes. Well, as I say, I think people who are working in the sort of shut up and calculate regime are fine to go on doing that. I don't think there's a problem with that. I think these kinds of concerns are relevant both for physicists and for philosophers who are interested in thinking about the measurement problem. I think the concern that I have about some current ways of thinking about the measurement problem is that these questions about sort of the epistemology and the nature of the evidence, I think, are often treated as an afterthought, and as sort of an assumption that, broadly speaking, if you can sort of derive the right mathematical structure of quantum mechanics out of your interpretation in some sense, then that's all fine. The evidence is going to work out fine. We're going to understand how the theory can be confirmed. And I think when you go and look at some examples of what people have done, I think you often find that's not true or not obviously true. That often they've arrived at something where it's actually quite hard to understand how the evidence for quantum mechanics could still sensibly provide support for it within the story that they're telling. So my take-home message, if you like, is that I wish people would take these issues a bit more seriously and treat them as sort of not just an afterthought, but one of the sort of central concerns that you should be thinking about when you're trying to solve the measurement problem. That really the measurement problem is in some sense all about understanding how to tell a consistent story about how our experiences and our outcomes, our measurement outcomes, are connected to the sort of theoretical entities.
Good. So I guess we can now turn to some of the approaches to quantum mechanics that you consider and discuss and how they relate to the measurement problem. I guess we probably don't want to get too technical here, but maybe if we get into a little bit of detail about some of the approaches. So do you mind sort of briefly introducing quantum bayesianism, cubism, and like what? And maybe the first question would be what issues do observer relative theories like this face, do you think?
Yeah, so quantum Bayesianism is a sort of generalization of a view in the philosophy of probability called Bayesianism or subjective Bayesianism. That's the idea that probabilities are nothing more than subjective degrees of belief. They're just measurements of how strongly you believe something. They're not anything more than that. They don't reflect any sort of objective feature of the world. So the subjective Bayesianist sort of seems to have a bit of a problem with quantum mechanics because quantum states seem to do very little else other than just kind of assign probabilities to things. So if you think all probabilities are subjective degrees of belief, it looks like you're going to be committed to saying that quantum states themselves are in some sense just kind of subjective records of degrees of belief. So the quantum Bayesianists have decided to embrace this. They say, yep, that's the right way to think about quantum mechanics. Quantum states are just about what you believe. They're just kind of tools or mathematical devices that you can use to encode what you believe about future events. They're nothing more than that. And that is supposed to help resolve some issues around the measurement problem, in particular, sort of common sort of testing ground for approaches to quantum mechanics and solutions to the measurement problem is in terms of what's called a Wigner's-Friend scenario. One of the problems we often encounter in a Wigner's-Friend scenario is that it looks like you have two agents who are going to end up assigning different quantum states to the same system. And so the quantum Bayesianists can quite straightforwardly say, well, that's no problem. They just believe different things. It's all subjective anyway. So that seems like a nice way of kind of resolving that problem.
Right. And do you think that's a viable response or no?
Yeah, I mean, I have difficulty sort of fully fleshing out the story of quantum Bayesianism in a way that makes sense to me. So the claim that probabilities and sort of quantum probabilities are purely subjective, I guess, could be read in two different ways, depending on whether you think these subjective probabilities are supposed in some sense to correspond to the actual relative frequencies that occur in the world. So, if you really think it's purely subjective and describes nothing at all, then it seems like you should say, well, quantum states don't actually correspond to any observed relative frequencies that we can't predict. We can't really predict relative frequencies with them. They record what I believe about the future, but they don't say anything about what the future is actually going to be, in a sense, independent of me. And I think that approach seems a bit hard to understand because relative frequencies are a really significant part of the evidence for quantum mechanics. We believe quantum mechanics is right because it predicts the correct relative frequencies. If you want to sort of sever the link between quantum states and relative frequencies, it becomes very hard to understand how any evidence could possibly support quantum mechanics. And so we do seem to have the sort of self-undermining problem that we've been talking about, where it looks like the interpretation no longer upholds the idea that the evidence for quantum mechanics is really evidence for it. The other possibility is to say that, in fact, even though the quantum states are subjective and in some sense, to be made clear, they are supposed to correspond to observed relative frequencies, so they are sort of a bit more concrete in that sense. But that seems to kind of interfere with what I've just said about the solution that the cubists are going to offer to Wigner's-Friend type scenarios, because if you have one of these scenarios and these two people assign different states to the same system, it seems as though you can now check because you can go and do some measurements and see what the relative frequencies are. And then if you assume that they're able to talk to each other, then they can compare and find out which of them is right. So either way, it seems like there's a sort of a problem in sort of fully understanding the story that's meant to be told here.
Right. So either the theory does predict that there be these observed, frequencies or so on, in which case you could get these conflicting results, Wigner's friend example, or it's not, it's just saying something about what's going on in their head or something like that, in which case, what is this a theory? How is this a physical theory in the first place? It seems a bit mysterious to me, but
right,
is that a fair way to put the concern there?
Yeah, exactly, yeah.
All right, fair enough. Okay, I guess we could move on to Everettian quantum mechanics, or sometimes called many worlds. Although I think some people like to draw a distinction there. And this approach could be criticized in several different ways, but probably the most pressing is that it doesn't seem to license the Born rule. So the theory should predict that long-run frequencies should converge with the mod squared amplitudes of the relevant wave function, but it's at best not clear how that arises, how we get that on Everett's theory. So is this that fair presentation? I mean, why do you think this is a very pressing concern?
Yeah, so I mean, the many worlds interpretation sort of solves the measurement problem by saying that there is no wave function collapse. When you do a measurement, all of the outcomes really occur. They just go off into sort of different branches of the universe. So anytime anyone does a measurement or a quantum observation, all of these branches are produced. So what that means is that anytime you do a sequence of measurements, every possible set of relative frequencies does actually occur in some branch of the universe. And so if they all occur, the question is, why should you believe that the frequencies you have seen are the ones that are likely according to the theory? And if you can't believe that, how could you possibly use your observed relative frequencies as evidence for anything? It seems like you need to have some reason to think that the frequencies that you personally have seen are likely to be special in some sense in order to believe that those frequencies can tell you something about the structure of the theory. So there seems to be a need for the Everettians to provide some quite strong and compelling reasons that we, as observers in an Everettian universe, would be justified in expecting to see relative frequencies which actually correspond to the predictions of the theory. And it seems, at best, very difficult to see how to do that, given that they are committed to the view that all of these things happen in these different branches. There's always going to be someone in each of the branches witnessing every one of those possibilities. So under those circumstances, why should you believe that you're the one who saw the accurate ones and everyone else is wrong?
Right. It's like we almost want to say that if you're, you should expect that the certain outcomes that should be much more likely, at least in the long run, but all the outcomes just occur. So in what sense are certain outcomes more likely or more frequently occurring?
It's very hard to make sense of probability at all in this context. Yeah.
Right. But as you discuss in the book, there have, of course, been some attempts to recover the Born rule. So there's decision theoretic approaches, self-locating principles, branch counting. Maybe we don't have time to get into significant detail, but could you talk a little bit about the approaches here and how you view their prospects?
Yeah, so most of these approaches are seeking to do is to show that you can derive the Born rule from the structure of the theory in some sense. And it certainly is true that you can set out a few axioms and you can show that the Born rule is in some sense kind of like structurally privileged inside the theory. I think that is sort of not in doubt. It's quite clear that there's a sort of privilege attached to that structure in the theory. So the question really is the way in which the Born rule features in the theory, does it feature in the right way to kind of justify the claim that you should in some sense expect that you're going to be in a branch which has the sort of high Born weight probability outcomes. And so my worry with all of these approaches really is that although I think they succeed in showing that there's some kind of structural privilege, to me at least it doesn't seem that any of them really succeeds in showing that there's the right kind of structural privilege which would justify me as an Everettian in believing or expecting that I'm going to be in the high amplitude branch. So for example, one particularly well-known approach is the decision theoretic approach. So this approach is based on proving a representation theorem. So what we do is we sort of set out a collection of axioms and we say, rational agents in an Everettian world are going to make their decisions in accordance with these axioms. And then we can do some math and we can show that if the agents do indeed make decisions in accordance with these axioms, they will appear as though what they're doing is maximizing utility with respect to some utility function and the probabilities predicted by the Born rule. So the point here is that an agent who obeys all of these axioms is going to behave as if they are treating the Born rule weights as probabilities. And so then I think that the hope is to sort of take a further step and say, well, that means they really are probabilities, problem solved. But I think there's various points at which you could criticize what's going on here. Many people have criticized the axioms themselves. It's not obvious that all of the axioms are really rationally compelling, that you have to obey them. Even if you sort of buy that it's in some sense compelling for agents to act in this way, there still seems to be a problem of making a connection between it's rational to act as if these sort of forward-facing weights are probabilities, and then sort of taking the further step to say it's rational to look back at what's happened in the past and believe that what you have seen is likely to be the high mod squared amplitude things. That seems to be taking a sort of unjustified step from what it's rational to do to what is rational to believe. And it's also making a sort of unjustified step from looking at the future to looking at the past in ways that don't seem to be backed up by what's actually happening in that proof. So although it's a very ingenious proof, I think it's a very clever idea. I'm not convinced that enough has been done here to really show that these probabilities as derived in the decision theoretic context are sort of robust enough to really play the role we need them to in the confirmation of the theory and in the epistemology.
Right, fascinating. And so more generally, well, I guess two things. One, how pessimistic are you generally that the kind of statistical postulate could be recovered from the theory itself without needing to be added as sort of an auxiliary assumption? Maybe you could talk about that first. Do you think there's some prospect for that, or what do you think?
I am very skeptical there's a prospect for that. Because in some sense, the statistical postulate is a sort of normative claim about what you should do or what you should believe. And in some sense, you're never really going to get a purely normative claim out of a sort of descriptive theory. So in that sense, it's sort of hopeless to think that you're ever going to get the statistical postulate out of just the theory. You are going to have to be adding some kind of sort of normative statement that requires the agents do certain things or believe certain things. That's what the role that sort of axioms are playing in the decision theoretic proof, for example. That's where the normativity is coming in. And the problem is that it's at least not obvious that there's any sort of normative claim you can put in that is going to be really sort of universally compelling and robust enough to really support the kinds of inferences that we want to make here. It seems as though certainly all the proposals I've seen seem to be relying on a sort of intuition or on sort of things that are controversial and that perhaps wouldn't meet with universal agreement. So that makes it quite worrying. It makes it seem quite unlikely that there's going to be a proof that's sort of really compelling enough to play the role we need it to play.
Yeah, I was thinking, does it really have to be that sort of robustly normative? I mean, if we just say, well, that the theory should predict that there'd be certain long-run frequencies, do we need to add something more about, well, this is what you should believe or something like that that's making maybe more explicitly normative? See what I'm saying? Do we yeah.
Yes. I mean, if I agree it would be really nice to get rid of the normative element, which I think is a bit uncomfortable from a scientific point of view. So what we would really like, I guess, would be to have the theory just predict that, yes, you will definitely see these long-run frequencies. But the theory can't do that. That's impossible because we know that the theory does predict that all of the other frequencies are found. We know the theory predicts that other people will see them. So it is never going to give us a sort of definitive prediction that you will definitely see certain long-run frequencies. So there is probably going to have to be some kind of normative element here in telling you what it is reasonable to believe or expect in this kind of situation, much as there is with other probabilistic theories, of course. And I think that the absence of any sort of well-defined single set of outcomes seems to make it more difficult, I think, to arrive at a sort of normative statement which everyone is going to agree on about what you should believe.
Fair enough. Yeah, I mean, I don't want to spend too much time on this, but is it... I mean, I could see someone saying maybe it's a little bit hasty to think that the only way you could recover the statistical postulate on the Everettian view is by making it something normative rather than being able to actually predict the long-run frequencies on the theory. Maybe that could be done. I don't know. maybe not. But I don't know why. Is it sort of appropriate to just rule it out at this point?
Well, I mean, whatever the sort of derivation is going to be, it's not going to be just sort of purely a prediction because, in a sense, we know exactly what the theory predicts. The theory predicts that everything happens, all of the frequencies happen. So you're never going to get the specific Born weight probabilities out as a bare prediction in the ordinary sense. So something else is going to have to be added to the story to explain why you are likely to be or why you should expect to be on one particular branch. And certainly in approaches to the Everett interpretation, which don't want to add additional structure that is going to single out some particular branch, sort of seems hard to see where that expectation could come from except from sort of our minds. The world itself, it seems, can't do anything to really make it the case that one of the branches is the real one. So in some sense, that's all got to be about you and not about the structure of the theory itself.
Right. I guess, I mean, if someone took some sort of branch counting approach and said look, for the different sort of paths along the branches, most of them preserve the sort of frequencies that you would expect and so on, or something like that. Is that not good enough? Or, I mean, if that could be done or
I think that still would not be good enough because, okay, suppose we posit some way of counting branches, sure. That still does not yet translate into a claim about what you will see or are likely to see. In order to get that, you would have to add some kind of like probabilistic selection mechanism where you're being dropped into one of the branches with some probability distribution. And certainly in the standard error interpretation, there is no such thing. You are not a sort of distinct thing over and above the wave function that is being dropped into some of the branches. You are just sort of composed by the branches in some sense. So I think in that case, you would still have the same kind of problem, that there doesn't seem to be any route from what the theory describes to a claim about what you are going to see or what you're going to expect. In order to get that, you would have to add some other mechanism that certainly is not there in the standard theory.
Right. Yeah, I was also kind of thinking that more generally about evident theory. Like, I mean, there's some nice things about the theory, right? I mean, by doing away with collapse, and I mean, you just have the unitary evolution of the wave function and so on. There's some nice things about it. Yeah, obviously there's some shortcomings. Maybe we think it's, well, there's the concerns we've been discussing here, but also maybe we think it's ontologically very not very conservative and so on. Maybe others concerns that might arise, but I don't know. It might be that the nice features about it make it worth taking very seriously. And I mean, what do you think? I don't. Do you think there's some?
I mean, I do think the error interpretation should be taken seriously. I think sort of at a technical level, it's the easiest one to make work. So that's a good reason to want to make it work. At the same time, I really do think these concerns about probability they're not a minor issue. And in particular, I think you can't sort of just say, well, that's a con, but there are some pros, so they balance out. These concerns about probability are about the sort of internal coherence of the view. They're about could we have arrived at quantum mechanics at all in Everettian universe? Can we still say the evidence supports it? And I think if the answer to that question is no, that's a fatal objection. You can't reasonably accept a view which sort of says internal to itself, well, you shouldn't believe this. If it undermines itself, we do have to reject it. So while I think we should take the error interpretation seriously. I think we should try to be solving these problems. But if we can't solve them, I don't think that's something that can be offset by the fact that it's nice in other ways, so that they have to be solved if the view is going to be viable.
Right. That makes sense. But what if someone were to say, okay, maybe we add it in as a further postulate, or maybe we have to modify the theory a little bit to recover it, but otherwise it could be mostly as it's already given. Is that worth exploring? What do you think? Yeah.
So I'm skeptical about just adding it in as a postulate inside the pure standard Everett interpretation, because I don't know what that postulate says. I find it really hard to formulate coherently what that postulate is actually saying. It seems to be a postulate that is purely about what you should believe or what you should expect. But I'm not personally really willing to accept that as part of a scientific theory, there's some kind of like primitive postulate about what you should believe that is not backed up by what's physically there. It's just a sort of brute fact that you're supposed to believe that. I want to be able to see how that's sort of derived from what's physically there in the theory. So the other option is to add something to the Everett interpretation to solve these problems. And I'm very open to that. I think that's an interesting thing that we should explore. I think one obvious possibility is a sort of single world Everettian approach in which somehow we have all the branches, but one of them gets selected at some point and made actual. That's all, I think, very appealing in some ways. It does, however, mean that as soon as you start adding things, you lose some of these advantages in terms of it being technically very easy, because once you've got new structures that you're adding in, you have to work out how to make those structures function properly in all the different regimes of the theory. So one of the main advantages of the Everett interpretation gets lost once you start adding extra structures.
Right. Yeah, what you said there about that potential interesting approach, it sounded in some ways where there's different branches, but one of them is sort of made actual, sort of reminded me a little bit of Bohmian mechanics. I mean, I don't know, is there a little bit of a connection there? And
yes. I
guess if you want, you could comment on Bohmian mechanics and how that might approach the measurement problem there.
Yeah, Bohmian mechanics is in a sort of way a bit like what I've just said. It does, all the Everettian branches are in some sense sort of present in the Bohmian theory because the wave function is there and all the branches are there and never collapses. But the Bohmian adds Bohmian particles, and those particles sort of play the role of picking out the actual branch which we experience. So the thought is that the world that we actually know and all of our experiences supervene on or are determined by these little particles that are traveling around through space-time. The wave function is there to sort of tell them where to go, guide them around, and that's why we get these sort of quantum behaviors, because the wave function and all of the branches are there in the background guiding the particles, but we do have those particles to sort of choose a single actual course of history. But, on the flip side, we then get sort of the problem that I just described. Once you're adding these particles, you now have a sort of a much bigger technical problem, because you have to get those particles or some analog of them to fit into any application of the theory you might have in mind. And so we know how to do that very well in sort of standard non-relativistic paradigmatic applications of quantum mechanics. We can describe all of those experiments using a Bohmian story quite straightforwardly, but it does seem to be a lot more difficult to generalize this sort of beyond those applications. In particular, once you start looking at quantum field theory, there doesn't seem to be any version of the Bohmian approach at present which works for all of quantum field theory. So there is still this quite formidable technical problem of figuring out how to get the thing that you've added to generalize across all applications of quantum mechanics.
Yeah, okay, fair enough. I just wanted to a question sort of as an aside. I mean, but it's important, I think. When we talk about probabilities here, of course, you mentioned this a little bit already. We can talk about frequencies. We can talk about subjective probabilities. I mean, do you have a preferred way to think about probabilities, or how would you approach just thinking about probabilities, especially as it relates to quantum mechanics?
Yes, I mean, I think that the understanding of probabilities is itself an important, outstanding problem, and I would like to get clearer on that too. I tend to think of many probabilities, at least, as being just subjective probabilities, in the sense that they sort of encode our ignorance over some underlying real facts. I think those types of probabilities are reasonably easy to sort of make sense of in terms of their sort of useful ways of reasoning that make good predictions in certain circumstances. But at least in quantum mechanics, there seems to be this other type of probability that we sometimes call objective chance. It sort of varies interpretation by interpretation, but at least some interpretations say that there are probabilities in quantum mechanics which can't be reduced to anything else. They're not just about ignorance of something that's underlying. They really are probabilities there in the laws themselves. And so if that's right, if that one of those interpretations is correct, then we are going to have something to say about what objective chances are. And I think that's a hard problem. I don't really know the answer to that. I do tend to think of laws more generally in a sort of all-at-once atemporal sense. So my suspicion is that the right way to think about probabilities, or objective chances at least, will also involve some kind of all-at-once atemporal story that is perhaps constraining relative frequencies across all of history or something like that. But yeah, I don't know the answer to that.
Good. Yeah, I mean, when we talk about objective chances as a consequence commitment of the theory, I mean, I sometimes think that maybe the fact that there are those chances there is sort of an artifact of how the theory is. I mean, so like it might be that the theory tells you how the world as at one time, and only gives you some expectations or probabilities about how it will be at some later time. And okay, so in some sense we have probabilities there. You can call them objective probabilities, but it's just in that sense just primarily an artifact of what the theory tells you, if that makes sense. I mean, I don't know. What do you think?
Yeah, it is very interpretation dependent. So, for example, one interpretation which definitely does posit objective chances are the dynamical collapse approaches. So those approaches do really envision, it's a state of the world at a time probabilistically collapsing to some position, and then a bit later probabilistically collapsing to some other position. And those approaches say is that those probabilities really are objective. They're not derivable from anything else. There's nothing else going on underneath to determine what will happen. They are pure chances. But there are other approaches where that's not the case. So the Bohmian approach, for example, does not have objective chances. Everything is fully determined by the initial state at the beginning of time. Another perhaps interesting way to get rid of some of the objective chances is to have some kind of retrocausal or two-state picture. So if you look at, for example, the two-state vector interpretation of quantum mechanics, you sort of start with a quantum state at the beginning of time and one at the end of time, and you involve both of those. One goes forward and one goes back. And you can see that at least some of the supposedly chancy events will turn out to not be chancy anymore once you add in that extra information from later in time. So certainly there's possibilities to get rid of the objective chanciness and hopefully end up with a theory of quantum mechanics that doesn't have that.
Right. And you also mentioned your sort of all-at-once approach to laws. I mean, could you briefly introduce that idea, and how might it be relevant for thinking about quantum mechanics and their measurement problem?
Yes. So, I mean, the all-at-once approach is, I guess, motivated by the observation that both in quantum mechanics and in other areas of physics, it seems to be the case that we're seeing a move away from sort of the paradigmatic time evolution picture, where you start out at the beginning of time and you just evolve forward and produce the rest of history. A lot of the laws we're seeing in quantum mechanics and elsewhere seem to be more sort of global or atemporal in various ways. So the thought, therefore, is that the laws of nature don't work kind of like a computer starting at the beginning and rolling forwards throughout history. Instead, the laws are going to apply all at once to the whole of history. I like to compare that to the rules of a game of Sudoku. So if you think about how the rules of Sudoku work, they don't start at the left and go towards the right. They just constrain the whole grid at once and tell you whether a solution is valid or invalid. So the thought is the laws of nature could work like that too. They could just constrain the whole of history and sort of dictate what solutions are allowed and which ones aren't. So the relevance of that to quantum mechanics, I think that the relevance becomes particularly clear when we start talking about quantum non-locality. So there are these non-local effects that we see in quantum mechanics in certain situations. Any interpretation of quantum mechanics, any solution to the measurement problem is going to have to say something about the nature of that non-locality. They all have their own different explanations of it. But one difficulty we frequently encounter is that it's quite difficult to explain those non-local effects in a way which is consistent with relativity, because it seems as though you need to sort of choose some sort of underlying preferred reference frame to sort of get a sensible description of these non-local effects. And once you do that, you seem to be sort of contradicting the relativistic claim that there are no preferred reference frames. So, a sort of outstanding problem for some solutions to the measurement problem is to account for these non-local effects in a way that doesn't end up positing preferred reference frames. And one, I think, very straightforward way to do that is just to get rid of time evolution. The problem really arises because you're trying to combine a standard time evolution story with non-locality, and that then requires you to have some kind of way of assessing whether events over here are simultaneous with events over here or not, so that you can decide what your ordered story is going to be about which one brings about the other one. As soon as you sort of give up on trying to tell that kind of ordered story where one thing produces the next thing, you can kind of get out of the problem that you've ended up in, because you still have non-local effects, but you no longer have to put them on a preferred reference frame. They just kind of get defined all at once by these all at once laws. So that looks like an interesting route to explore as we try to solve the measurement problem, because it looks like a sort of straightforward way to reconcile these non-local effects with other theories of physics like relativity.
Right. So just on the all-at-once approach to laws first, when you talk about them constraining what sort of solutions are possible, stuff like that, how do you view the relation? I don't know if you think about a lot of the stuff that comes up in thinking about laws, like humanism versus non-humanism and other disputes come up there. But I mean, is it a sort of robust sense of constraining, like an anti-Humeanism would say, or how would you put this, do you think?
Yeah, I mean, the constraint viewpoint, as I and others have developed it, is intended to be a non-Humean view. So yeah, Humeanism is the view that the laws of nature are essentially just descriptive. They're just the best summaries of everything that's actually happened in the world. And one thing that's very nice about Humeanism is that it's very flexible. Anything you could kind of write down as a nice description of things is allowed to be a law on most Humean views. That contrasts with a lot of non-Humean views are not very flexible. A lot of non-Humean views have been developed with time evolution in mind. So, for example, the universals account says that laws are relations between universals. There are a few sort of paradigmatic classical physics time evolution laws which can be put in that form, but as soon as you go beyond that, you encounter a whole bunch of laws that are really hard to put in that form. And in particular, if you don't want laws to work in a time evolution way, if you want something a bit more atemporal, a lot of traditional accounts of laws of nature seem to really of sort of non-Humean accounts of laws of nature struggle to allow you to do that. So the sort of the constraint formulation that I and others like Eddie Chen have worked on was intended to be a reaction to that and to provide a more general form of non-Humean view where the laws are still sort of meaningful and robust and are responsible for the way that things turn out, but where you're allowed to be more flexible about what those laws can look like. They don't just have to be time evolution laws.
Right. Yeah, I mean, generally, I kind of like the all-at-once sort of approach, but I do find the anti-Humean commitments here a little bit mysterious. So without getting too much on this, I mean, a few weeks ago, I did have Barry Lohr and Tim Adlam on to talk about this, and so some of the stuff came up there. We could take a look at that. But the primary concerns for me is that I don't really understand what a law is supposed to be here and how it's supposed to play this role of constraining or guiding or anything like that. And I don't know, okay, do you sort of see where that concern might be coming from? And maybe if you could talk a little briefly to that.
Yes. I mean, I think one way to think of what the laws are doing in this situation is to think of them as defining like the space of possibilities. So, how did the universe come about? We don't know. We're never going to know that. But presumably there's some kind of like space of possibilities from which the universe is drawn. Like there's, whether you think those possibilities are just logical or you think there are some stronger constraints, in some sense there's got to be some kind of limitations on what could possibly have been realized. So I like to think of the laws as sort of being there in some sense defining whatever that space looks like, such that when the universe comes into being, it has to be drawn from a space of possibilities that kind of makes sense. You might think of the laws in that sense as being a bit like if you think about sort of a mathematical space, when you're looking at mathematical spaces, there's going to be certain rules for things that can exist within that space. They wouldn't be the kinds of entities that they are if they didn't obey certain properties that make it possible for them to exist within that space. And so similarly, I would say in the constraint picture, the laws are playing that kind of role and just defining what the possibilities are, and then however the universe comes into being, it's sort of drawn from those possibilities.
Right. Okay, that makes a bit of sense. I mean, there would be some more things I want to say about modality and possibility and so on that probably would take us a bit of far afield for now. So I think I'll for now move on. Yeah. So I guess we could look at a little bit more of a couple more of the approaches you consider in the book. So one sort of interesting, but in my perception under discussed approach is called superdeterminism. It's a local deterministic hidden variable theory, but drops measurement independence. So there could be sort of pre-existing correlations between the measurement settings and earlier states, something like that. I mean, you could correct me if I'm not stating it quite accurately, but anyway, you note that this approach requires finely tuned initial correlations, which brings certain concerns of its own. So I guess could you talk a little bit about superdeterminism here and some of the issues there with the finely tuned initial correlations, and what is that?
So superdeterminism is not in and of itself a solution to the measurement problem, but it is certainly related, and it's intended as a way of dealing with this problem of non-locality. So the thought is that, well, we can get rid of non-local effects if we say that the preparation of the particles that we start with and the choices that people make later about what measurements to perform, if we allow that those things are like correlated with each other in certain sort of non-trivial ways, then we can write down a model of these situations which does look completely local, so we don't get sort of weird spooky actions at distance or anything like that. So where do those correlations come from? And there's the different versions of superdeterminism, but at least the sort of naive original version says the correlations were just there in the initial state at the beginning of time. There's no deeper explanation for them. They just there like that at the beginning of time, and then they evolve forward to produce the correlations that we need when we do the actual experiment. So that is supposed to be a sort of solution to the locality issue. The worry I have with that approach is that in general, we don't like the initial state of the universe to contain fine correlations. We need, in fact, the initial state of the universe doesn't contain a bunch of too many fine-tuned correlations, because all of our scientific methodology relies on that. So in particular, when we're sort of doing things like consulting records. In order to consult a record and interpret it as providing information about the past, you have to assume this record was most likely produced by a human being in the past deliberately recording the result of the experiment. It was not produced by the particles just randomly deciding to rearrange themselves to produce something that looks like a record. Why should we believe that it's the human and not the particles rearranging themselves? Well, usually the explanation that's given there goes back to what's known as the past hypothesis, which is an assumption about the initial state of the universe. Like, roughly speaking, it's the assumption that there weren't a lot of very sort of fine-tuned correlations in the initial state. And so you're very unlikely to have particles randomly rearranging themselves to produce things that look like records, because to get that, you would need to have a bunch of very specific correlations in the initial state. So it does seem really methodologically important from the point of view of doing science that in general, we're going to assume there aren't going to be lots of fine correlations in the initial state. So superdeterminism, it doesn't literally contradict that, because it's sort of logically possible to say the initial state has all of the fine correlations needed to make superdeterminism work, and no other fine correlations. But I do find that quite awkward as a position to hold, and I worry that it's a bit unstable, because it doesn't seem like you have any good reason, once you've accepted that there are some of these fine correlations, for sort of ruling out all the ones that would cause really big problems with scientific methodology. So I think you would need a really good, clear, strong principled reason for positing those special fine correlations, because otherwise you're going to end up in this problem where you don't have good reason anymore to rule out all the other correlations that you don't want.
Right. I think I recall you saying that something to the effect of that if you have, it requires certain sort of correlations and not others, that sort of pushes against the naturalness. I recall you saying something to that effect. What does that? What does that mean?
Yeah, I mean, naturalness is a word used in physics, particularly for distributions of parameter values, but one can also apply it as a description of the initial state, saying that the initial state is natural. It means something like saying that the initial state is the kind of state you might expect to get if it was drawn at random from some kind of simple uniform distribution or something like that. And so if you draw at random from a simple uniform distribution, what you're going to get is a state which mostly doesn't contain fine correlations of the kind that you need for superdeterminism or for books randomly rearranging themselves to produce records. So the worry here is that if you're going to take superdeterminism seriously, it seems you need to deny that naturalist assumption. You do need to say, well, no, the state wasn't drawn in this kind of natural way. It does have these specific fine correlations, but at the same time, we're still not going to allow it to have all these other fine correlations. So as I say, that's not necessarily a logical contradiction, but for sure, those positions seem to be sort of pushing against each other in uncomfortable ways.
Right. Does superdeterminism involve something? Well, does it involve retrocausality or something like that, or not? Is it just correlations?
No, I would personally sort of present superdeterminism and retrocausality as two alternative approaches, and they're both quite similar in that when we come to describing what happens in the sort of quantum non-locality experiments, both of them do want to say, okay, there are correlations between the state at the initial preparation and the measurement choice you make later, but they differ in how they explain that. So superdeterminism, the explanation is, well, these correlations have just been there since the start of time, just sort of waiting to be realized. Whereas in retrocausality, the explanation is there's a backwards in time causal effect such that your choice later on causes the state to be whatever it is earlier. So sort of mathematically, they look quite similar. You still end up with these two things being correlated, but sort of the explanation that's being given is different, and thus also the epistemic concerns that might arise are going to be different because the mechanisms aren't the same.
Right, good. That makes sense. And then, so what about retrocausal approaches? I mean, I guess you could talk about how that relates to the measurement problem, but also, I mean, some people are going to just balk at them saying, look, retrocausation is almost incoherent, or perhaps is incoherent. Causation is essentially temporally asymmetric. I mean, so I guess you could comment on that and then the connection to the measurement problem.
Yes, I mean, there's several different motivations for positing retrocausality in quantum mechanics. One is, as I've just said, because you're worried about non-locality and you want to get rid of it. But more broadly, there are motivations connected to the all-at-once type of views that I've been discussing, because if you have a view where the laws of nature operate all at once in some sense, then causation is going to be a sort of emergent feature, and the asymmetry of causation is going to be an emergent feature that's not really there in the laws. So in some sense, in that kind of all-at-once picture, there are sort of generic retrocausal effects in the sense that sort of things depend on each other in a mutual reciprocal way, and there isn't really a sort of directed causation going in either direction. So those are sort of two different motivations for positing retrocausality. I personally am not that convinced by the first motivation, because I'm not convinced that non-locality is such a bad thing and that we should be worrying too much about trying to get rid of it. But as I say, I am very sympathetic to the all-at-once style approaches. So for that reason, I do think that retrocausality as part of an all-at-once approach is worth investigating and can potentially help us address some of these conceptual challenges.
Right. And then for the worry that, well, some people just think that retrocausality doesn't even make sense. I mean, what do you think about that?
I mean, I guess there's two things you could mean by that. One thing is that you could think that causation is just by definition something that goes forward in time. And I'm not here to have arguments about the definitions of words. So if you want to define it that way, that's fine. But then I would just say there's some other kind of modally robust effect that goes backwards in time. Call it what you like. The other, I think, more serious concern is the worry that if we have both forwards causation and backwards causation, you can get various kinds of paradoxical effects. So you're going to get sort of contradictions. A common example is the grandfather paradox, where you imagine like a time traveler going back in time and killing their own grandfather before the grandfather is able to father any children. So then the time traveler won't exist. And I do think that is a genuine concern. I think if you're going to posit retrocausality, you do need to make sure you're doing it in a way that isn't going to lead to obvious logical contradictions. But it does seem to me that doing retrocausality within an all-at-once style picture mostly gets rid of those kinds of concerns, because the point of the all-at-once picture is that the whole of history is being selected together. So it will sort of, by construction, be self-consistent with itself. You can't really have a situation where you get a contradiction because the whole thing has been chosen in this consistent way. So I think that when done right, retrocausality is not going to run into those kinds of problems, but certainly it's important to be aware of that and think about it in your construction of a retrocausal model.
Right. Good. So let's see. I guess this is the previous chapter, but you also talk about like primitive ontology approaches or programs. I guess we've covered this a little bit already, but maybe if you could talk generally about what that sort of program is and how it, because I do want to talk about fundamentality and levels and so on a little bit as well. So maybe introduce that a little bit.
So primitive ontology is a sort of class of approaches to quantum mechanics which want to solve the measurement problem by telling some reasonably straightforward story about some classical-ish ontology which lives on space-time and moves around or is defined in a sort of straightforward way. So, for example, the de Broglie-Bohm or pilot wave interpretation is a primitive ontology approach. The Bohmian particles are the ontology. They're just kind of traveling classical trajectories along space-time. It's pretty straightforward. Similarly, the GRW collapse approaches can be formulated as primitive ontology approaches. You can either do that by thinking of the ontology as some kind of mass distribution over space-time, or as some sort of collection of point-like events scattered across space-time. But either way, you have something effectively classical that's just distributed across space-time in a sort of straightforward way. So the primitive ontology approaches are nice in a sense because they do seem to solve many of the kind of epistemic concerns I've been raising. They have this very straightforward story to tell about what measurement is, about what the world is, and how we get access to it. So it seems much easier to understand how to tell that kind of story in the primitive ontology approaches. But on the other hand, because necessarily the primitive ontology approaches do involve adding something that isn't there in the standard formalism of quantum mechanics, that does mean you sort of run into these technical problems that we have discussed, where it becomes difficult to extend them to cover all of the applications of the theory, because you have this extra thing you've put in that you're going to have to reconcile with every different application.
Right. I'm sorry, wait, what's this extra thing you have to put in?
So whatever your primitive ontology is extra. There's nothing if you look at pure unitary quantum mechanics, there's nothing there that could be described as primitive ontology. There's no particles moving around on space-time or mass distributions or anything like that. So if you want to put in some sort of well-defined, somewhat classical ontology that just lives on space-time, you are going to have to add something.
Right. But I mean, is that necessarily a problem? Like, I mean, someone could say that sometimes it's worth it to add in these posits to our theory because of the explanatory work that it could do or solving certain problems. I mean, Do you think that's a plausible reply on behalf of them? Yeah.
For sure. I'm not against doing that. But I think, if you are going to do that, then at some point, eventually, you're going to have to show that you can make it work for the whole theory, for all of the applications of the theory. And the problem right now is that none of the approaches we have at the moment do work for all of the applications of the theory. And then I think there are sort of structural facts about quantum field theory in particular that make it difficult to make any such thing work throughout all regimes of the theory, make it perhaps feel a bit unlikely that anything is going to work throughout all regimes of the theory. So, I don't want to say it's impossible, but I do want to say there are reasons to be perhaps nervous about the possibility that no such thing is going to work in the long run.
Right. Okay, fair enough. And then you also talk about scales and fundamentality. And how do you think these things, relate, and how would maybe characterize fundamentality especially?
Yes, fundamentality is an interesting one. So I guess traditionally we have had a close association between scale and fundamentality. We have assumed that the smallest things are the most fundamental, and everything happening at sort of larger scales is in some sense derived from whatever is going on at the smaller scales. And there are good historical reasons for that. Perhaps the strongest argument for that is the observation that, in general, if you look at sort of the relationship between the microscopic and the macroscopic in classical physics, what you'll find is that one possible macroscopic state could correspond to lots of different microscopic states. So given the microscopic state, you can work out what the macroscopic state is, but not vice versa. So that does kind of make it look like, okay, the small stuff is what's really there. It's determining what happens at large scales. What happens at large scales doesn't determine what happens at small scales. So that is the traditional view. There are good reasons for it. I have argued in various places that perhaps, particularly within quantum field theory, there are maybe some reasons to start being worried about that way of thinking about fundamentality. We start to get some quite strange effects in quantum field theory that perhaps look as though the traditional relationship between scales and fundamentality is being subverted in some sense. I think there are also features of the mathematical structure of QFT specifically that perhaps make it more feasible in those kinds of regimes to say, well, maybe the large stuff determines the small stuff rather than vice versa. So that's a bit speculative, but I think there are at least reasons to, as we go around trying to figure out what we've got wrong about quantum mechanics and what we can change to make sense of the measurement problem, maybe one thing to look at is this sort of assumption about the relationship between scale and fundamentality.
Good. Yeah, and definitely a lot worth exploring there. I guess I've always been a little bit skeptical of some of the stuff people say about fundamentality. After all, I don't know. There's smaller or larger things. There's different ways we might describe the world, and they might relate in interesting ways. But it's not clear to me what fundamentality talk is sort of adding on top of that, on top of, say, more or less coarse-grained ways of describing things, or talking about things on smaller or larger scales. I don't know. Do you see what I'm getting at there? And
yeah, but I think the word fundamental is used certainly in complicated and somewhat ambiguous ways in physics. I think in general, fundamentality is closely tied to explanation. The thought is that whatever is most fundamental is where the explanation stops. You can't explain further. So you're making a decision about where you think the explanations should stop. And whatever view you have of explanation, I think it's worth looking at different possibilities for what those fundamental things might be, because different choices of what is fundamental are going to lead you to different classes of what the explanations available to you are. We often find that certain choices lead to much better and more powerful and more unifying explanations. That gives us kind of a good reason to say, okay, well, maybe that thing is really fundamental or is comparatively more fundamental, because taking that approach makes our explanations much better and simpler and more unifying. So I think, for me, I ultimately end up thinking about questions about fundamentality as being, in effect, questions about explanation and what explains what and where should our starting point be.
Yeah, that makes sense. So then, of course, we have to then think about explanation more rigorously, I suppose. Right. And then you also talk about single world realist consistent histories approaches, SWRCH. Could you introduce that a little bit, and why might that be a different, approach to the measurement problem?
Yeah, I mean, that's kind of motivated by the view that we sort of briefly discussed earlier, the idea that you could have an Everettian view and just select one of the histories and have that be the actual world. And so if there's a way of doing that consistently, that would be a nice way of avoiding the probability problems, because there would be some actual outcomes to which probabilities could be attached. So consistent history seems like plausibly the right kind of formalism to use there, because as you can tell from the name, it's all about histories. Basically, the formalism gives you a way of defining histories composed of a series of events, and it gives you certain conditions that you can look for in sets of histories, such that that the set is what's called consistent, meaning roughly that you can treat the mod squared amplitudes that are assigned by the theory as probabilities. They're going to sort of add up as probabilities in the usual way. They're going to be normalized in the right way. You can think of them as being like classical probabilities. So when you have a sort of consistent set of histories, you can imagine potentially one of those histories being probabilistically selected and made actual in some sense. So that looks like possibly a route towards kind of solving some of those Everettian problems while retaining some of the sort of structure that they have. So in some sense, we still keep all the branching structure. We just, at the end, or in a sort of atemporal sense, select one of those histories and make it actual.
Right. It does seem a little bit, I don't know, maybe this is just me, but it seems maybe a little bit mysterious to me. Like, well, what is it that makes, or what is it that could even make one of these histories the actual one? I don't know. It just seems to be a little bit, maybe that could be supplied by a theory, I suppose, but yeah.
Well, I share that sense, but also I think that question is just very similar to like the question of why is there something rather than nothing? Something made something actual somehow at some point. No theory of physics has an explanation for, how it is that there came to be an actual world. It seems to me unlikely that any theory of physics is really going to answer that question in any depth. And so, I share the sense of mystery, but I'm not sure that the consistent histories is worse off in that sense.
Right. So you're saying it just might be that that's where explanation runs out, so to speak. This is the yes, sort of history that there is.
Insofar as that seems to be, if there's a process of some kind that selects and actualizes an actual history, that's all going to be happening outside of the universe in a way that is completely inaccessible to us from within the universe. So it's hard for me to see how we could plausibly go about inquiring what that might look like.
Right. Yeah, I guess there's a lot of things that I could ask more questions on, but just kind of generally then, this to save quantum mechanics from the measurement problem, can you sort of summarize what we need here? We need some sort of package deal. What do we need? What does it need to do, just generally?
Yeah, I think the way I see the sort of field of existing solutions is that we have these sort of two classes. We have the sort of roughly primitive ontology style approaches, and those ones I think sort of make more sense, and from a sort of epistemic point of view, they do kind of overcome the epistemic difficulties I've talked about, but they still have a lot of technical problems in being expanded to quantum field theory and other things. So that's a reason to be worried about those ones. The other ones are the ones that I would call unitary only, the ones which don't really add anything to the standard unitary formalism of quantum mechanics. So that includes the Everett interpretation, also relational quantum mechanics, also maybe cubism, these kinds of things. And those, I think, are easier to make them work technically, but then they do encounter all of these epistemic problems. And I personally am skeptical that there's a solution to those epistemic problems. I think the problems are quite deep in the sort of structure of quantum mechanics and the fact that it doesn't really provide any means of representing the event of actually getting a measurement outcome. So I'm skeptical that any of those is going to work out in the long run. So it seems to me that probably what we need is something that is not quite unitary, that does move away from just the pure formalism of quantum mechanics. But we know that adding things, it leads to technical problems. So ideally, we probably want to be adding as little as possible. So it seems to me that probably the right route forward is going to be looking at perhaps different types of ideas of what we could add to the theory in a way that is going to resolve these epistemic problems, but is going to be sufficiently minimal that it's not going to break everything when we try to go to quantum field theory or whatever. So I think one route I find interesting is a sort of generalization or alteration to relational quantum mechanics, which involves adding in some relationships between what's observed by one observer and what's observed by another observer. So adding in those relationships does, it seems to me, solve most of the epistemic problems that have been encountered. And that does leave us with the technical problem of how to make that work. But because it's quite a minimal thing to add in some sense, it seems perhaps more hopeful that we can make this work beyond the sort of paradigmatic cases, as opposed to approaches which are adding particles or collapses or something quite substantive, which it seems more difficult to generalize.
Right. So I guess two things then. I mean, you mentioned a couple potential or interesting approaches there, but I mean, do you have a preferred approach, or what do you think is maybe most promising? And then second, what's the sort of way forward? How do we try to make progress on this?
Yes, I don't know if I have a single approach which I would put all my money on. I have a sort of idea of the space of approaches that I find compelling, partly for the reason we've discussed. I think it's very likely the right approach is some all-at-once style approach, which will incorporate some kind of retrocausality or sort of reciprocal effects across time, which will probably incorporate some kind of relationality, which will probably incorporate the addition of something to the standard formalism in order to sort of solve the epistemic problems. And so I think that space which I've just described, there are existing approaches in that space, but I would say all of that space is quite underexplored compared to the other things we've talked about today. So, I think the way forward really is for more attention to be paid to that particular sort of space of solutions, which has the potential to avoid the problems that we've been discussing today. I think there are really interesting possibilities there, and we need more people thinking about them and working on them to sort of figure out if they can be made to work.
Awesome. Yeah. So I do normally end with a kind of more metaphilosophical question about the value of philosophy. And I mean, it's sort of interesting because like a lot of the stuff you discuss in this book that we've been covering today it's stuff to do with physics, but it's not really separate from certain philosophical issues, especially some of the stuff that came up. So I don't know, do you mind commenting a little bit about the value of philosophy, and maybe especially in the value of philosophy for thinking about physics and foundations of physics and this sort of issue?
Yeah, I mean, I was originally a physicist. I did my PhD in physics, and I moved into philosophy because I think that the kinds of questions which I'm interested in and which I think are very important for the progress of physics, a lot of them are philosophical in nature, and so I think there's a real need for more consideration of those problems from a philosophical but physically informed point of view. And one of the things I like about the measurement problem is that I think it's a case where there's really sort of fruitful possibilities for sort of interplay between these fields. Because I think the solution to the measurement problem probably is relevant to future physics and to quantum gravity and so on going forwards. And I do think that particularly these kinds of epistemic concerns do constrain those solutions and guide us towards those solutions in useful and helpful ways. So I think there's really a really nice opportunity here for philosophers and epistemologists to sort of help shape that discussion and help guide the solution to this concrete physics problem in a way that I do believe can contribute to the process of physics. So for me here, it's a really nice example where these are not just sort of idle intellectual questions. This is a case where philosophy and epistemology really does impact very, very concretely on real science and hopefully on further progress in science.
Awesome. Yeah, I totally agree. I mean, it seems pretty clear, at least to me, that if we're thinking about epistemology and how we conduct inquiry and how we're thinking about some of these foundational issues, I mean, if those are philosophical issues, and to some extent they are, then that's important for thinking about the science and so on. So yeah. Yeah. All right, I think that's been really good. I'll draw the questions to an end there, but thanks so much for coming on, Professor Adlam, and taking my questions and writing this book. Yeah, it's been awesome. So again, I'll include links to where people can find it.
Sounds great.
It's awesome.
Thanks so much.